So welcome everybody to this video from 162 Maths, where we will go through the AQA AS Maths paper of 2023, paper 1, section B, which is the mechanics section. A reminder that a link to the paper along with the question breakdown so you can see easily which topic each question is from can be found in the description, along with a link to the 162 contents page where you have access to AS Maths lessons, revision resources and all walkthroughs from the past papers. Let's look at question 12. A particle initially at rest starts to move forward in a straight line with constant acceleration a meters per second squared. After 6 seconds, the particle has velocity of 3 meters per second. Find the value of a. Now with the question where it talks about acceleration, we're looking for the type of acceleration it has, and it has constant acceleration, which means we're referring to the Suvat equations. So having the letters of Suvat at the side to then find within the question which of the pieces of information we have and which is the piece of information we want to find out. So looking through, we are told initially at rest. That means if it's initially at rest that the value of u is 0. We're also told 6 seconds. So that means that time t is 6, and we're also told that at that time the velocity is 3 meters per second. So our final velocity v is 3. The question is asking us to find the value of a, so we'll just keep that in there as our variable that we need to find. So using those 4 variables, we identify the Suvat equation that has u, v, a and t. And for that Suvat equation, we're using v equals u plus at. We're wanting to identify a, so your 2 options are to substitute values in that we have. 3 is equal to 0 plus a times by t, so 6a. Or you could rearrange v equals u plus at and make a the subject. So that would be v minus u divided by t is equal to a. And you can substitute those values into here as well. 3 minus 0 divided by 6 is equal to a. We can see that in the first example you would need to do a bit of rearrangement. So 3 is equal to 6a. So 3 divided by 6 is equal to a. And same here, we end up with 3 divided by 6, which is equal to a. So 3 divided by 6 is equal to a. Both of those values found are 0.5, which is our correct answer, 0.5. Looking at question 13, it says a resultant force of -2.6 newtons acts on a particle. The acceleration of the particle is -6y meters per second squared. Find the value of y. We can see that it mentions force and acceleration in this question. So we're looking at the use of F equals ma. Force equals mass times acceleration. If we use the vector for force of -2.6 equal to mass times by our acceleration of -6y, we can then set up an equation based on the -2 and -6. So -2 is equal to m times -6. Solving for m, -2 divided by -6 gives us a value of 1/3. Positive, since both negatives cancel each other out. For our second part of this question, we want to find the value of y. Now we know that m has a value of 1/3. we replace m with that value of 1/3, we can now use that to work out y. So 6 is equal to 1/3 of y, which means 6 times 3 is the value of y, which is 18. Question 14. A ball initially at rest is dropped from a vertical height of h meters above the Earth's surface. On the diagram, I've got the horizontal for the Earth's surface and the vertical for the height from which the ball is dropped. As the ball is being dropped, it is going to fall under gravity, and gravity will be the acceleration in this question. Since gravity is constant, it is another SUVAT question. So again, we're picking out the variables for SUVAT and looking in the question to find what these are. So initially at rest, meaning our velocity for u would have a value of 0. We've got a time of 4 seconds, so t is equal to 4. We have gravity is the value for acceleration, and since g for gravity is in the answer, we can leave g as our variable. And the value of s for our displacement is given in some information here. It says after the 4 seconds that the height of the ball is now at 0.2 h meters, which will be above the Earth's surface. So if we consider where that would be, so after 4 seconds, our ball is at 0.2 h, meaning that in those first 4 seconds, the displacement has happened here. So our displacement in those 4 seconds is 0.8 h. Now we have 4 pieces of information to put into our SUVAT equation. So using the SUVAT equation, s equals ut plus half at squared, we can substitute our values in and show our answer h equals 10g. So 0.8 h is equal to 0 times 4, which is 0. That is equal to half of a, which is our gravity, times by t squared, which is 4 squared. 0.8 h is equal to half of 16, which is 8g, and the question wants us to show that h is equal to 10g. So dividing 8g by 0.8 gives us 10 and g at the end. Part B says, assuming air resistance cannot be ignored, explain the effect that this would have on the value of h from Part A. Air resistance is going to slow the ball as it drops, and so the answer to Part B is going to be that air resistance causes h to be less. Question 15. A particle is moving in a straight line such that its velocity v meters per second changes with respect to time t seconds, as shown in the graph below. Part A wants us to show that the acceleration of the particle over the first 4 seconds is 3.5 meters per second squared. The thing to remember with this question is that acceleration is the same as the gradient. So acceleration is the same as the gradient of the line. And in order to find the gradient of the line in the first 4 seconds, we want to find the change in velocity and divide that by the change in time. and we can get both of those pieces of information from the graph. So the change in velocity from -4 all the way up to 10, that change is equal to 14. And the change in the time, that takes us from 0 seconds to 4 seconds. So that has a time change of 4 seconds. That calculation, 14 divided by 4, is 3.5. In part B, it says the particle is initially at a fixed point P. Show that the displacement of the particle from P when t equals 9 is 62 meters. So for graphs that are velocity time graphs, the displacement is linked with area. As the graph starts from a negative velocity, what we want to find then is the displacement of the first triangle, the second triangle, and the rectangle. Or we may wish to find the area of the triangle and all of the trapezium together. So the triangle and the rectangle here make up a trapezium. So we could work out the area of this trapezium and the tiny triangle. Or we could use our SUVAT equations to help us find some of these values out and bring everything together for our displacement value. If I look at the first part of the graph and look at the part where we have constant acceleration of 3.5. So if we take that first part and use SUVAT, we can get the information from the graph. So our initial velocity is -4, our final velocity is 10. Acceleration we know is 3.5 from the part A, which is a gradient, and the time that takes is 4 seconds. So we have a choice really in order to find that displacement value. So for any of the SUVAT equations that involve S, and we can then take a pick because we have all 4 pieces of information. So if we were to take So the choice is yours for which SUVAT equation to use. I'm going to use v squared equals u squared plus 2as to find that value of s. So v squared is 100, u squared is 16, 2 times a is 7, and then we get s. So 100 minus 16 over 7 is the value of s, and s has a value of 12 meters. So our first displacement area is 12 meters. Our second displacement area is found from the area of this rectangle here. Now, if we were to use the SUVAT equations this time, the acceleration would be 0, and the reason the acceleration is 0 is because we can see that velocity doesn't change. So instead, let's just find the area of the rectangle. So the area of the rectangle is 5 times by 10, which is 50, and that would be 50 meters. Bringing both parts together, we have the displacement of 12 meters plus the displacement of 50 meters, which gives a total of 62, which we were trying to prove. Question 16. A toy remote control speedboat is launched from one edge of a small pond and moves in a straight line across the pond surface. The boat's velocity v meters per second is modelled in terms of time t seconds after the boat is launched by an expression v is equal to 0.9 plus 0.16t minus 0.06t squared. Find the acceleration of the boat when t is equal to 2. The first thing to recognise is this is not a SUVAC question because our velocity is based on a time, so it has an expression which involves t. If our expression for velocity involves t, then we're going to be using differentiation and integration. Acceleration is the change in velocity over the change in time, which means if we differentiate our expression for v, we will get an expression for a. So differentiating our expression, we get 0.9 differentiates to 0, 0.16t differentiates to 0.16, and differentiating the last term, we get 0.12t. With that expression, we can then use the substitution for when t is equal to 2. So since t is equal to 2, acceleration is 0.16 minus 0.12 multiplied by that 2. That gives us an acceleration value of negative 0.08, and the units are meters per second squared. In 16b, find the displacement of the boat from the point where it was launched when t is equal to 2. For displacement from the expression from velocity, we want to integrate, since displacement is velocity integrated with respect to time. So if we integrate the expression given, so 0.9 plus 0.16t minus 0.06t squared, and we integrate that with respect to t, we get an expression for our displacement. So let's do that. So the first term gives 0.9t, the second term is 0.16t squared all divided by 2, and the third term 0.06t cubed all divided by 3. We must make sure we put plus c when we integrate, and tidying the expression up, 0.9t plus 0.08t squared minus 0.02t cubed plus c. We then need to look for what information we have in the question to determine the value of c. In the question, it tells us that initially, so that means t is equal to 0, it's initially launched from the edge of the small pond, so its displacement is 0. If t was equal to 0 and we substituted it in to these three parts here, and the answer is equal to 0, then that tells us that c must also be 0, because all of these terms would equal 0. So that gives us an expression to use. And the question asks us to find this displacement value when t is equal to 2. So we have a substitution that we can use to work out our displacement. So s is equal to this calculation. And that gives us a displacement value of 1.96, and the units for that is meters. What's useful to know if you're looking at a variable acceleration question is the link between displacement, velocity and acceleration, and if you need to move down from displacement to velocity, or velocity to acceleration, you are going to differentiate. If you're going to move from acceleration to velocity or velocity back to displacement, you're going to integrate. And that's a really useful way of remembering which way you're going to do those questions. Question 17. A particle P is initially at rest on a smooth horizontal surface. A resultant force of 12.9 newtons is then applied to P so that it moves in a straight line. Find the magnitude of the resultant force. For part A, the magnitude of our resultant force takes the 12 and square it, the 9, square it, add them together and find the square root. That will give us a value of 15 newtons. Question 17b, two fixed points A and B have position vectors OA, which is 3, 7, and OB, which has vector k, k-1, with respect to fixed origin O. P moves in a straight line parallel to AB. Find AB in terms of k. So the first part we want to look at finding the vector A to B. To travel from A to B, we're going to travel back along the vector OA, but in its opposite direction, and along the vector OB with the direction it's going. And so we can have OB subtract OA. And a nice way to look at that is the vector which is A to B. If you start with that second letter B, that's OB, minus the first letter A, minus the OA. Let's put those vectors together. So k, k-1, subtract OA, which is 3, 7. And then we're just going to collect those two parts together, k-3, and we've got k-1 minus 7, which is k-8, and that is A to B in terms of k. In question 17b, it tells us that P moves in a straight line which is parallel to AB. So for the second part of the question, it's wanting us to find the value of k. Now, if it's moving parallel to AB, then what that deduces is that our vector must be a scalar multiple So what that means is our vector, which is k minus 3 over k minus 8, that vector must be some multiple of the vector 12, 9. So k minus 3 is equal to some multiple of 12, and k minus 8 must be some multiple of 9. Now we've got two unknowns here. We've got this lambda notation, which gives us our first unknown, and we also have our k value, which is our second unknown. And when two unknowns appear in two equations, we can solve those simultaneously. So the process of simultaneous equations can be sped up through the use of a calculator, because you've got the function on your calculator to solve that simultaneous equation. Just watch how you input those values in, because you may need to rearrange the equation in order for it to match how your calculator wants it presented. But once you do so, you can get a value of 23 for k. It only wants us to find k, doesn't require the value of lambda, so that's not needed. Question 18. A rescue van is towing a broken down car by using a tow bar. The van and the car are moving with constant acceleration 0.6 meters per second squared along a straight horizontal road. In the diagram below, you've got that picture. We've then got information about the van, it has a mass of 2,780 kilograms. The car has a total mass of 1,620 kilograms. Then we have the forces acting on the van, which is a driving force, the resistance force for the car, and also the van. 18A says the tension in the tow bar is modelled by T equals KD minus 18, where K is a constant and we need to find K. So the first thing I like to do is to get a diagram and simplify that by just having just some boxes, and we can add in the arrows for the different pieces of information that we've been given. So we've got the mass of the van, which we can have as our force that acts down, and that is 2,780 multiplied by G for gravity as our force. The car, we're told, has a total mass of 1,620 kilograms, so its force 1,620 G for gravity, that force. Now what we also have is that these are forces that are Newton forces. We're then told about the driving force of the van that is going to act forwards. That has been given a letter D. We've then got some information about the resistance force. This is for the van. So it has a resistive force of R newtons. It says that the car also has a resistance force of 0.6 R newtons. So these are all our forces. We also have tension acting in the tow bar, and that acts in both directions. Reasons for which we can talk about for part B. Now there are forces that are acting against the mass, and we call those reaction forces. Now normally we give those the reaction forces 1 and 2, but since the question has got a resistance force labelled R, and we've got the same R with the car resistance force, these extra R for reaction forces that have been drawn into the diagram may not be helpful to be seen all the time. So I've just popped those in pencil just so that you can see that they would normally be in our diagram, but we're not going to use them for part of this. The other thing to make sure we've got is our acceleration, and that we can include in our diagram with that double arrow, and we've got 0.6 and the units we're told meters per second squared. So in this question we have a lot of variables with R, and we've got T for tension, we've got D for this driving force, and so we're going to end up using some simultaneous equations to solve this question. So it's worth 5 marks, so there's quite a lot that needs to be done. So what we want to think about is taking the van and its forces individually, the car and its forces individually, and you can think about the whole system as well. So there's 3 equations that we can begin with. If we consider what's happening in the van, which is at the front of our diagram, using F equals ma is where we want to be thinking about our force going forward just on the van. We have that driving force D. Our resistive forces that are on the van we have the force R, which we need to subtract because it's going in the opposite direction to which the van is moving. We also have the tension, which is in the opposite direction to which the van is moving. So all of the forces acting on the van, we've got our driving force, our resistance force and our tension force, and they're acting forwards for D and in the opposite direction backwards for R and for T, so that's why we are subtracting those. That's our force overall minus our mass of a van, which is 2,780, times by acceleration, which is 0.6. So that's for the van. If we consider the car, again we're using F equals ma, and we want to look at all of the forces that are acting in the direction of movement. So the only force acting in the direction of movement is tension. And we're subtracting the force in the opposite direction, which is 0.6 R. That's the only force acting in the opposite direction to movement. And that for the car is equal to its mass, 1,620, times by acceleration of 0.6. So we've got individually the forces acting on the van and individually the forces acting on the car. If we were to think about in total the whole situation of the car and the van combined, let's put this answer down here. So if we look at the combined car and van, and we were to consider F equals ma again, we then have got all of the forces acting forwards, which is our driving force, and all of the forces acting backwards, which is our resistance force on the van, the resistance force on the car, and then we're looking at the combined mass of 2,780 and 1,620, which is 4,400 kilograms. So that would be 4,400 times by 0.6 for the acceleration. So there's all of the forces going forward and all of the forces going backwards. Now, although we've got tension in the middle, which is the force acting both forward and backwards, they're going to cancel each other out in that process because we would be adding tension and subtracting tension, so they would cancel each other out. So combined, we've got car and van using F equals ma there. Now, the tidy up of that would be D minus 1.6 R equals 4,400 times by 0.6. If we take the van and rewrite that, so we get D minus R minus T, and do the calculation 2,780 times 0.6, we're going to get 1,668. So that's the van. If we do the car in the same way, T minus 0.6 R equals 972. And if we did combined, together that would be D minus 1.6 R equals 2,640. Now it says that you can replace t with kd minus 18 at any stage. I'm going to, for now, try and solve these simultaneously. I'm going to use the car and the combined equations to do so. The first thing I want to do is eliminate r. And just like a simultaneous equation, if we were to eliminate r and make the coefficient of r the same value, we would take the first equation and multiply by 1.6. And if we take the second equation and multiply by 0.6, that's going to give us the same coefficient of r. And then we can eliminate r by subtracting those two equations. So I'm going to do that now. So it would be 1.6t minus 0.6 also multiplied by 1.6r equals 972 times 1.6, which is 1,555.2. If I take the second line and multiply by 0.6, we get 0.6d minus the 1.6 times 0.6r equals 2,640 times 0.6 is 1,584. And what that's done is it's allowed the coefficient of r to be the same in both of these equations, because it would be 1.6 times 0.6, and the signs are the same, so we are going to subtract those simultaneous equations. So if I subtract the first line away from the second line, we would get 0.6d minus 1.6t. The coefficients of r would be the same, so that would give us a coefficient of 0, so we won't write that in. And then the subtraction on the right hand side would give us 28.8. Now it's at this stage that I'm going to replace t with what it gave us in the question. So 0.6d minus 1.66 lots of t, and t we were told is kd minus 18 equals 28.8. So I've replaced t in this equation with kd minus 18, which was given to us in the question. So we just continue on. So 0.6d minus 1.6 kd plus 1.6 times 18, which is 28.8, equals 28.8. If we subtract the 28.8 on this side, on the left side, from the right side, we end up with a value of 0. So 0.6d minus 1.6 kd equals 0. Subtracting 28.8 away from both sides leaves us with 0. At this stage you could factorise out the letter d, or you could take the 1.6 kd on over to the right hand side. We want to find the value of k, so 0.6d divided by 1.6d is equal to k. The letter d will cancel with each other, leaving 0.6 over 1.6, and that has a value of 3/8. Finally, 18b says state one assumption that must be made in answering part A. So that is in reference to the tow bar. So our assumptions about the tow bar are usually the same in these types of questions. So we can assume that the tow bar is rigid, or that the tow bar is inextensible, meaning that tow bar isn't going to compress in any way or stretch in any way, and so we haven't got to worry about any additional forces. We could also say that the tow bar has negligible mass. Meaning we don't have to take the mass of the tow bar into consideration as part of our questions. They're very typical in the way that these can be answered in this last part, so making sure that you're using the correct words for these assumptions.